So, hello students. Today we're going to discuss some important questions regarding your chapter atoms. So, let's have an overview of the chapter. So, this chapter will give us knowledge about the discovery of constituents of atom in various models, which is proposed by physicists like Rutherford and which has been given by Rutherford's model. Then, few drawbacks that are present in the model, and how Bohr improved his model and removed the limitations, and then the absorption emission spectra, distance of closest approach, nuclear size, atomic size, radius and velocity of nth shell of an atom, energy of an nth shell of an atom, then emission spectra of hydrogen or H-like atoms, Ripple formula. In this, in the board exams, this chapter has got questions of like 1, 2, 3, and 5 marks. And this is an overview of a chapter. No, sorry, not overview of a chapter. It's an overview of a distribution of marks, how the marks will be distributed. Um, in your board exams. So 1 marks questions, you'll have 18, which makes total 18 marks. Then section B will have 2 marks each, that makes total of 14 marks, 7 questions. Then section C will have 15 marks in total, 3 marks each and 5 questions. Section D will have 15 marks as well in total, but it will have 3 questions of 5 marks each. And section E carries 4 marks and you have 2 questions. Okay, so what are the crucial topics that have been covered in this chapter? Rutherford's model's drawbacks, observation and conclusion, Rutherford model correction by Bohr, Bohr's model and its limitations, absorption and emission spectra, derivation of radius, velocity, and energy of nth shell of an atom, and 5 famous spectral lines series of H or H-like atom like Lyman, Balmer, Bastian, Brackett, and P1 series, and determination of wavelength of emission of light due to electron excitation and de-excitation. So here, first of all, first question that we have is that what is the ratio of radii of the orbits corresponding to the first excited state and ground state in H atom? Now we know uh, Bohr's radius can be given as Rn is equal to E naught h square n square by pi m square, which is directly proportional to n square. So for first excited state, we'll have n is equal to 2. So for excited state, excited state, and this is our first excited state, the value of n is 2. And for ground state, the value of n is 1. So the ratio of radii of orbits, so the ratio, let's say this is, so our R2 will be equal to 2 square is equal to 4, and R1 will be equal to 1 square, which is equal to 1. So therefore ratio will be given as R2 by R1 is equal to 4 by 1, or which is 4 is to 1. Moving on to the next question, which is using Bohr's postulates of atomic model, derive the expression for radius of nth electron orbit, hence obtain the expression for Bohr's radius. So centripetal force provided by the electrostatic force of attraction, the centripetal force okay, which is provided by the electrostatic force of attraction, can be given as mvn square by rn square, which is equal to e square by 4 pi epsilon naught r square. And from Bohr's second postulate, we have ln is equal to mvn, rn is equal to nh by 2 pi. So let's keep this as equation number 1 and this as equation number 2. Now Vn can be written as Vn is equal to nh by mRn 2 pi. So now putting the value of Vn in equation number 1, we have putting the value of Vn in 1, we'll have mRn and h by mRn 2 pi whole square, which is equal to e square by 4 pi epsilon naught r square. So now solving this for the value of Rn, we'll have Rn is equal to E naught n square h square by pi m e square. So this is our basically fundamental expression for Bohr's radius. So for n is equal to 1, for Bohr's radius n is equal to 1, for Bohr's radius, which is n is equal to 1, we'll have R1 is equal to E naught h square by pi m e square. This is the end of our solution. Now in this question, it's given to us that if the series limit frequency of Lyman series is nu L, then what will be the limit frequency of p-fund series? Okay, so we know that 1 by lambda is equal to r 1 by n1 square minus 1 by n2 square. And for Lyman series, we know n1 is equal to 1 and n2 is equal to infinity. So 1 by lambda L is equal to r 1 by 1 square minus 1 by infinity square, which is equal to r, or 1 by lambda L equals to r. So let's keep it as equation number 1. Now for p-fund series, n1 is equal to 5 and n2 equals to infinity. So we have 1 by lambda p is equal to r 1 by 5 square minus 1 by infinity square, so which will give us 1 by lambda p is equal to r by 25. So let's keep it as equation number 2. Now putting the value of equation number 1 in equation number 2, we'll have 1 by lambda p is equal to 1 by 25 lambda L. Now again we know again we know that nu is equal to c by lambda. So this implies lambda will be equal to c by nu. So hence we can also write it as nu p by c is equal to 1 by 25 nu L by C. Cancel C on the both sides, which becomes nu P is equal to L by 25. This is the end of our solution. Next question is that write two important limitations of Rutherford's model of atom, and also we need to discuss that how Bohr resolve it. So basically his atom, especially atom, basically his model of atom to be precise, basically failed. First of all, it failed to explain the stability, to explain the stability of atoms, stability of atoms. Then also arrangement of electrons in circular path was not defined. The path was not defined. Arrangement of electrons in a circular path was not defined. So any particle that was moving in a circular path will undergo acceleration and it will radiate energy, and thus revolving electron will lose energy and finally fall into the radius, and hence the entire system will collapse. So, and now how did Bohr resolve it? So basically it was a very interesting thing that how Bohr resolved it. Actually what Bohr did was, Bohr said that in his model that electrons revolve around the nucleus in a fixed orbit and they do not lose their energy, and hence Bohr resolved the limitation. So now moving on to the next question, which is a 12.5 electron volt beam is used to bombard gaseous hydrogen atom at room temperature, up to which energy level of the hydrogen atoms would excite it. Calculate the wavelengths of first member of Lyman and first member of Balmer series. So we know that energy of electron in nth state of an atom, nth state of an atom is given by minus 13.6 that square by n square electron volts. Now here Z is our atomic number, as we all know that, and for hydrogen Z is equal to 1. So now let's calculate the energy required to excite an atom from initial state to final state. Energy required to excite an atom from initial state and I to final state and F to final state. So this is equal to minus 13.6 by NF square plus 13.6 and I square volt. Okay, So now this energy must be equal to or less than the energy of the incident electron beam. So therefore we'll have this as, this implies minus 13.6 by nf square, this 6 by nf square plus 13.6 by ni square electron volt. Now this will be equal to 12.5, which is the energy of the electron. So not the energy of the electron, so energy of the incident electron beam. So now we'll have this as, this implies minus 13.6 nf square plus 13.6 is equal to 12.5. Because it is for the ground state, so for ground state we know I initial, this one is 0, initial state, not 0, 1, so there we have 13.6. So now this implies 13.6 minus 12.5, which is equal to 13.6 nf square. So now I'll repeat again why we took ni as 1 is because firstly it's going from the ground state to the upper states. So we know in the ground state ni will be 1, so 1 square is equal to 1, and put it there. And solving this will give us nf is equal to root over of 13.6 1.1, which is equal to 3.51. Now which is approximately 3. Therefore nf is equal to 3, and hydrogen atom will be excited up to third excited state. Hence hydrogen atom would be excited up to third energy level. Third energy level. Okay. Next, let's calculate the first member of Lyman and first calculate first member of Balmer. So first member of Lyman series can be given as 1 by lambda h is equal to rh 1 square, 1 by 1 square minus 1 by 2 square. R equals 0.097 into 10 to the power of 7 inverse, and lambda is 1.5 angstrom. And now for Balmer series, first member of Balmer is equal to h1 square 1 by 2 square minus 1 by 3 square is equal to lambda will be equal to 6563 angstrom. So this is the end of our solution. So now we need to state the Bohr's quantization condition for defining stationary orbits, and how does de Broglie hypothesis actually explain the stationary orbits. So actually it's a very interesting um, very interesting question actually. Pretty simple, directly theoretical. So here Bohr's quantization condition basically says that of all possible circular of all possible circular orbits allowed by the classical theory, the electrons are permitted to circulate only in those orbits in which the angular momentum of an electron is an integral multiple of h by 2 pi, where h is Planck's constant. H is Planck's constant. So for any permitted orbit, so basically for any permitted orbit, we'll have L is equal to mvr is equal to nh by 2 pi, where n is equal to 1, 2, 3, and so on, and lmv and r are angular momentum, mass, and the speed of electron respectively, and r is basically the radius. Now this above equation is Bohr's famous condition, quantum condition, where electron of mass m is confined to move on a line of length L with velocity v, and then the de Broglie wavelength associated with the electron will become lambda is equal to h by mv h by p, where p is linear momentum. So p will be equal to h by lambda is equal to h by twice L by n, which is equal to nh by 2L. Now when electron revolves in a circular orbit of radius r, and then this would imply that 2L is equal to 2 pi r. So therefore P equals to nh by 2 pi r, or basically PR is equal to nh by 2 pi, and this is the end of this question. Okay, so in this question, we have been told to find out that using Bohr's postulates derive the expressions for the frequency of radiation emitted when electron hydrogen atom undergoes transition from high energy state when electron in H atom jumps from the energy state n is equal to 4 to n is equal to 3 to 1, and identify the spectral lines to find the emission to find which the emission line belongs. Okay, so firstly, we noted the radius of electron orbit is given by r equals n square h square divided by 4 pi square k m e square. So let's keep it as equation number 1. And kinetic energy of electron ek is equal to 1 by 2 mv square is equal to ke square by r. Using equation 1, we get ek, that is putting the value of r in here, that is h e square 4 pi square 4 pi square, then k m e square by n square h square, and then we have the potential energy ep equals minus ke square by r. Now putting the value of r here, we'll have this is equal to minus ke square multiplied by 4 pi square k m e square by n square h square. So this will be equal to minus 4 pi square k square m e to the power 4 divided by square h square. Now let's calculate the total energy of the electron. We have calculated the kinetic energy and potential energy. Now let's calculate the total energy of an electron. Total energy of electron equals 2 pi square k square m to the power of 4 by n square h square minus 4 pi square k square m e to the power of 4 divided by n square h square, which is equal to minus 2 pi square k square m e to the power of 4 divided by h square multiplied by 1 by n square. Now according to Bohr's frequency condition, whenever electron in hydrogen atom undergoes transition from higher energy state to lower energy state, we have when hydrogen atom undergoes transition h nu em minus enf. So this is equal to minus 2 pi square k square m e to the power of 4 by h square, sorry, by h square multiplied by 1 by nf square minus 2 pi square k square m to the power of 4 by h square multiplied by 1 by ni square. Now taking this term common from both of the sides, this term common, this term, taking this term common, will have h nu equals 2 pi square k square m to the power of 4 by h cube multiplied by 1 by nf square minus 1 by ni square. Here then nu will be equal to 2 pi square k square m to the power of 4 by h cube multiplied by 1 by nf square minus 1 by ni square, which is then equal to nu equals to c 2 pi square k square m to the power of 4, which is when we multiply c on both the numerator and denominator, ch cube multiplied by 1 by nf square minus 1 by ni square. Now here um, this part this part is known as our Rydberg's constant. This r is known as our Rydberg's constant, Rydberg's constant, and the value of r is 1.097 into 10 to the power of 7 per meter. So therefore nu equals to rc multiplied by 1 by multiplied by 1 by nf square minus 1 by ni square. Now for higher state, now in higher state, now higher state ni is equal to 4 and lower state nf equals to 3 to 1. For a transition, ni is equal to 4 to nf is equal to 3, which is Paschen series. Ni equals 4 to nf equals 2, which is Balmer series. Ni equals 4 to nf equals 1. So this is our Lyman series. This is the end of our solution. Now let's have a summary of whatever we have done. So atom as a whole is electrically neutral and therefore contains equal amount of positive and negative charges in Rutherford's model. Most of the mass of the atom and all its positive charge are concentrated in a tiny nucleus, typically 1 by 1000 the size of an atom, and the electrons technically revolve around this. And Rutherford's nuclear model has two main difficulties in explaining the structure of atom: that it predicts that the atoms are unstable because the accelerated electrons revolving around the nucleus must be spiral into the nucleus, This contradicts the stability of matter. Second, that it cannot explain the characteristic line spectra of atoms of different elements. And atoms of each element are stable and emit characteristic spectrum. The spectrum consists of a set of isolated parallel lines termed as line spectrum. It provides useful information about the atomic structure. To explain the line spectra emitted by the atoms as well as the stability of atoms, Niels Bohr proposed the model for hydrogenic single electron atom. And lastly, some words about our institution. So we work at here at Clavictor Academy Private Limited. It is a startup incubated and supported by the Foundation for Technical and Business Incubation, NIT Rourkela in Odisha, and it is recognized by the Startup India and Startup Odisha programs and has received various awards for its innovative learning platform Clavimate. It is focused on improvement of the Odisha State Board education system by providing high quality education content at the fingertips of the student. Its team comprises of young and dynamic alumni from prestigious institutes of Odisha such as NIT Rourkela, Veer Sindhusai University Technology Burla, and Government College of Engineering Kyojhar. So for admission and other information, you can contact this number that is being shown on the screen. So here's the end of the video. Thank you very much. Have a nice day.